record on this chapter. All right. So today I start with summarizing the Lagrangian formulation of classical mechanics. First, we define a Lagrangian function in terms of the kinetic energy and potential energy of a given system. For example, a single particle moving in space. Now, note that the Lagrangian function will, in general, have explicit time dependence if the particle is in an external time-dependent field. Okay. However, in this course, we will concentrate on those cases without explicit time dependence most of the time. Okay. For each path xt connecting the two space-time points, in the starting point and also the destination, we introduce the action functional st, which is defined as the integral of the Lagrangian over the time variable t, the time t. This functional depends upon the entire path xt. All right. So we know that there are many paths connecting the two space-time points, the initial point and also the destination. However, the most important path that we're interested in is the classical path. This classical path is the one on which the action gives an extremum value. All right. All the other paths will not give an extremum value of the Lagrange of the action. Along this classical path, the Euler-Lagrange equation is obeyed, which is given in equation 2. Right. Now, if the kinetic energy is given by 1/2 mx dot square and V is equal to Vx, we can easily determine that the rank L rank x dot equal to mx dot, rank L rank x equal to minus rank V rank x. Substituting these two expressions into the equations 2, which is the Euler-Lagrange equation, we will obtain a familiar equation in equation 4, which is just the Newton's second law of motion. Okay, and I would like to point out that the term rank L rank x dot is known as the generalized momentum of the system. In fact, in terms of the Cartesian coordinates, rank L rank x dot is actually equal to mx dot, the linear momentum of the particle. All right. Now, for a system of n particles, the same procedure will give a set of n Euler-Lagrange equation motions. All right. Of course, in general, these n equations are coupled to each other because the particles are interacting with each other. All right. And we can also define rank L rank x dot I, rank L rank x dot I as the momentum, okay, generalized momentum, all right, for the particle I. Now, I would like to point out that there may exist a more general, a set of more general independent coordinates, which I call Q1, Q2 up to Qn, all right? Now, in other words, we can express these n Cartesian coordinates in terms of these n independent coordinates or variables. All right. And then one will ask, will the Euler-Lagrange equations have a very different form? The answer is no. The Euler-Lagrange equations have exactly the same form if the n Cartesian coordinates are replaced by any general set of n independent coordinates. All right. And the rank L rank Q I dot gives you the generalized momentum associated with the generalized coordinate Qi. Now we take a look at this example. We consider a particle moving in a plane in the presence of a potential. In the Cartesian coordinates, the Lagrangian is given by equation 7. The first part is the kinetic energy, and the second part is the momentum. Okay. The second part is the potential energy. Then the corresponding Euler-Lagrange equation of motion are mx double dot equal to minus v minus x, my double dot equal to minus round v round y, right? Which are identical to Newton's equation of motion. We can also use the polar coordinates, and the Lagrangian will take this form given in equation 10, and we follow the same rule, the same general rule about deriving or obtaining the Euler-Lagrange equation of motion. First, we take the rank L rank R dot and obtain mr dot, and then differentiate these results with respect to t. On the right-hand side, we differentiate L with respect to R. It turns out that there are two terms derived from equation 10. One is from the potential energy, the other one is from the kinetic energy, all right? And we can do the same thing for the coordinate theta and theta dot. And we can see that mr dot, mr squared theta dot are the generalized momenta, all right? In the radial direction and in the angular direction. And the rank v rank theta is the top, the generalized force in the theta direction, all right? Now suppose if v is independent of theta, then in equation 12, the right-hand side of equation 12 will be equal to 0. In other words, there's no dependence on theta. And this theta is called a cyclic coordinate. And we can easily see that the presence of a cyclic coordinate, or the vanishing right-hand side of equation 12 ensures that there exists a conserved quantity, p theta, all right? Now, in this example, we can use both Cartesian coordinates and polar coordinates. And which one has an advantage? If we have a central potential, obviously the polar coordinates will be preferred. All right. Otherwise, either case will be acceptable. On the other hand, if we go back to the double pendulum case, if we go back to this double pendulum case, we realize that there exists only two independent variables or two independent coordinates in the system, phi and psi only, right? If we use the Cartesian coordinates to study this system, eventually we realize that two of the four coordinates are redundant, are not independent from the other two. Okay, for example, we can easily see that x1 squared plus y1 squared equal to L squared. So this is our constraint equation. Y2 squared plus x2 squared will give you another constraint, all right? So we have four Cartesian coordinates with two constraints. So actually we have only two independent variables or coordinates. And after all the simplification, we realize that they are the two most convenient or most favorable independent variables are phi and psi. Okay, so the concept of generalized coordinates is very useful because generalized coordinates must be the independent variables of the system or independent coordinates of the system. All right. If you insist on using Cartesian coordinates all the time and derive the corresponding Euler-Lagrange equations in Cartesian coordinates, it will be okay. All right, you get four in this special example. You will get four coupled Euler-Lagrange equation motions. However, two of them are actually the constraints equations. And finally, after some elimination of some redundant variables, we get back to the two equations, the two Euler-Lagrange equation motion in phi and psi. So either way will be fine, okay? However, I strongly recommend you to follow the rules, follow the procedures that I outlined in the notes. First of all, write down the write down the Lagrangian in terms of kinetic energy and potential energy defined in Cartesian coordinates, because we are all familiar with Cartesian coordinates, and it is easy to identify the kinetic energy and potential energy with respect to some familiar coordinate systems. All right. After doing that, we try to list all the relations among these Cartesian coordinates so that we can identify some suitable or desirable generalized coordinates. All right. After doing that, then we can re-express the Lagrangian, in terms of the generalized coordinates. All right. After having the Lagrangian written in terms of the generalized coordinates, then we can write down the Euler-Lagrange equation motion very easily. Right, following the rule number 3, or its generalization to n particles. Okay. So this is my recommendation for you. Don't. It is preferable to identify the generalized coordinates as early as possible. All right. Okay. Now, yes, according, as shown here, I emphasize that the Euler-Lagrange equation of motion have the same form, no matter which set of coordinates you use. For example, if you use n Cartesian coordinates, then you will have n coupled differential equations. If you use n independent coordinates, again, generalized coordinates, then you also have n independent equation of motion. All right. Now, it is important to point out that very often, the n Cartesian coordinates, not all the n Cartesian coordinates are independent. All right. Say, for example, in the case of a double pendulum, in fact, we have only two independent coordinates. So if you choose to use generalized coordinates to express the Lagrangian, you realize that only phi and psi, the two independent variables, will appear in the Lagrangian function. However, if you insist on using the Cartesian coordinates, you will have four Euler-Lagrange equation of motion. However, among the four, two of the equations will give you the constraint equations only. All right. However, if you express the Lagrangian function in terms of phi and psi, the generalized coordinates, you obtain two independent Euler-Lagrange equation of motion. Is it clear? Okay, let me see some questions here. Can the expression of kinetic energy used in the Lagrangian function derived without using Newton's laws? Now, the definition of kinetic energy and potential energy has nothing to do with Newton's second law, right? Newton's second law tells you give you the equation of motion, all right? And in Lagrangian formulation, again, the definition of kinetic energy and potential energy does not give you the dynamics, does not give you the equation of motion. The Euler-Lagrange equations give the equation of motion of the system, which are identical to the Newton's second law, right? Can you follow? Any more questions regarding the how to show that the Lagrangian is Galilean invariant? I will answer this very soon. All right. So up to now, about the Lagrangian formulation of classical mechanics, do you have any questions? So up to now, instead of accepting the Newton's equation motion, which is supported by empirical evidence or experimental evidence, we follow or put forward our fundamental principle, namely the principle of least action. All right. We just follow the rules, and we can derive the equation of motion right away. And these equation of motion are exactly the same as the Newton's second law of motion. All right. So the whole thing becomes following a recipe. Okay, the recipe of Lagrangian formulation. Any more question? If not, then I will continue. Okay, let me continue. Okay, here I will talk about some conservation laws and symmetry of the system. Now somehow we here I skip all the steps about deriving the Lagrangian, expressing the Lagrangian, and also deriving the or spotting the generalized coordinates. Somehow you can all do it. All right. So write down the Lagrangian in terms of kinetic energy and potential energy in Cartesian coordinates, and then we impose include all the constraints relating the coordinates, different coordinates, so that only the generalized coordinates will appear in the definition of Lagrangian. And then we derive the Euler-Lagrange equation motion, all right? And the Euler-Lagrange equation motions in terms of these n generalized coordinates are given in equation 1 here, all right? Pi, rank L, rank Qi dot, is defined as the generalized momentum associated with generalized coordinates Qi. Okay, we look at different Lagrangian. First, Lagrangian being independent of generalized coordinate Qi. Okay. Now keep in mind that the generalized coordinates are different from, in general, are different from the Cartesian coordinates or cylindrical coordinates or spherical coordinates. All right. As in the example of double pendulum, the generalized coordinates are the angles, phi and psi. All right. And you can see that the phi and psi are angles and have different dimensions in comparison to the Cartesian coordinates x and y. Okay, so this is very important in Lagrangian formulation. Generalized coordinates, in fact, represents the so-called independent, really the fundamentally independent variables of the system. All right. Okay. The first example, a Lagrangian, which is independent of generalized coordinate Qi. All right. So in this case, we know that rank L, rank Qi must vanish. Okay, must vanish. So in equation 1, we can see that this term will disappear. All right. So we are left with this. So the time derivative of the generalized momentum is equal to 0. In other words, the generalized momentum is a constant or is conserved. An example of such a Lagrangian is the motion of a particle in the absence of a force, free particle. All right. So you can the Lagrangian consists of kinetic energy only, and the corresponding generalized momentum is given by rank L, rank V vector equal to mv vector equal to constant. Okay, and we all know that this for a free particle, the linear momentum is conserved. All right, which is consistent with the first law of Newton's Newton's first law of motion. As a result, we can conclude that if L does not depend on Qi, the conjugate generalized momentum is a constant motion. All right. The second example, Lagrangian, which is independent of time t. So it does not depend on time at all. It depends on qi and q dot I only. All right. So in this case, we realize that rank L rank T must vanish because it does not depend on time explicitly, right? And if we want to find the differential of L with respect to T, we will apply the chain rule, since L is a function of Qi and Q dot I only, and Qi and Q dot I are functions of T, all right? So we apply the chain rule here. And the first term due to Qi, the second term due to Qi dot. Right. So we take a close look at the first term. According to the Euler-Lagrange equation of motion, the rank L rank Qi is equal to this, okay? The Euler-Lagrange equation of motion, all right? So if I move this to the right-hand side in equation 1, then rank L rank Qi is equal to rank d by dt rank L rank Qi dot. So by making use of the Euler-Lagrange equation of motion, we can rewrite the first term in this form, all right? And we can also rewrite the first term once again in terms of these two terms, because we can take Qi dot and rank L rank Qi dot as a product of two variables or two functions, all right? And differentiating a product of two functions with respect to t will give you two terms, 1 and 2, all right? So this term is equal to the difference of these two terms. Now there are three terms in this expression. Now the second and third will cancel automatically. So we are left with this, all right? And we realize that rank L rank Qi dot is the generalized momentum, Pi, all right? If I move the right-hand side to the left-hand side, or move the left-hand side to the right-hand side, we realize that the total time derivative of the combined expression, which I called H, must be independent of time. In other words, it is a constant, all right? It is conserved. And this H is known as the Hamiltonian of the system, all right? In the case of Cartesian coordinates, the Hamiltonian becomes a very familiar quantity, the total energy of the system, including both kinetic energy and potential energy, all right? So in conclusion, we realize that the law of energy conservation arises from the homogeneity of the Lagrangian with respect to time, all right? So the H or L is independent of time. The third example, Lagrangian being independent, the Lagrangian being independent of absolute position of a system of particles. In this case, the Lagrangian depends on the relative coordinates and not the absolute position of each particle. All right. So if we make a translation, an infinitesimal translation, all right, then we expect that the Lagrangian will be expressed in this form. The original L before the shifting, and the change of L, the change in L due to the infinitesimal translation. All right. Now, here we say that the Lagrangian is independent of the absolute position of the particles. In other words, the shifting or the infinitesimal translation will not change the value of the Lagrangian, right? Because the relative distance remains the same. So we require that L plus this infinitesimal correction equal to L. In other words, we have to require round sum over I, round L, round Qi, equal to 0 automatically, okay? Because epsilon is an arbitrary quantity, arbitrary parameter. So in order for this sum to vanish, in order to have this term to vanish, we have to require this term, this total sum, to be equal to 0, all right? And we know that sum over I, round L, round Qi, give you the total linear momentum of the system. And here it tells us that the total linear momentum is conserved, all right? So the requirement that the Lagrangian is homogeneous with respect to spatial translation gives the law of conservation of linear momentum, all right? So let's summarize. Independent of generalized coordinates, then we have a conservation of generalized momentum. Right? Lagrangian independent of t, independent of time, will give you conservation of energy. Lagrangian being independent of the absolute position of a system of particles. In other words, the Lagrangian depends only on relative distance, relative coordinates. Then we will have conservation of total linear momentum, all right, of the system. Now, without looking at the solution, let's try to work out this exercise. In this example, we have a Lagrangian which is independent of the orientation of the whole system in space. In other words, if we perform an infinitesimal rotation to the system, the Lagrangian remains unchanged. All right, the Lagrangian remains unchanged. Now, this property will give us the so-called conservation of angular momentum. Okay, now we all know that this is true because even in Newtonian mechanics, we know that we can derive the same conservation law as well. But in Lagrangian formulation, we realize that the conservation laws is directly, closely related to the symmetry possessed by the Lagrangian. All right. So here, after rotation, we have a change in L, an infinitesimal change in L. This infinitesimal change can be expressed in terms of the chain rules. given here. By Euler-Lagrange equation motion, we can rewrite the first term as this, all right? And the second term as this. And we apply the special property of triple product of vectors. We can rewrite the two terms as this, all right? And collect the and factor out the quantity delta theta hat. We realize that rank L rank VI vector is equal to the generalized momentum, all right? Since delta theta is an arbitrary quantity, so we require that if the Lagrangian remains invariant under rotation, this generalized momentum, i.e. the angular momentum, must be conserved, all right? So the invariance of the Lagrangian under rotation give us the conservation law of angular momentum, right? Okay. Thus epsilon depends on I. Now here, we shift the coordinate system, all right? Shifting all the particles by a small distance. In other words, we just shift the coordinate system, whether it is Cartesian, spherical, or cylindrical coordinates, by a small distance, all right? So the displacement will appear to be the same for all particles, all right? So that's why epsilon is independent of I. I here means the particles, all right? Okay, here I give you the definitions. Here. All right, differentiating with respect to a vector actually is a shorthand notation, all right? Actually, it means this, the gradient. Gradient, all right? A gradient. Can you follow? Okay. Now, let me come back to the question about Euclidean invariant. Is the Lagrangian Euclidean invariant? This relates to this example, example 3. All right. Now, Euclidean invariance means that if we let's see, the laws of physics will remain unchanged with respect to different inertial frames, right? Euclidean invariance. So let's see. Let's see. I think I have to think a little bit more about this. Um, 陳欣望, can you ask, can you repeat your question more explicitly? I'm afraid that I may misunderstand it. Can you tell me your question once more or more clearly? Hello? Hello? 陳欣望, are you there?
Hello. I mean, in the first lecture, when you are talking about the Lagrangian, and you said that since the physics is the same, if we shift the coordinates, then we know that obviously the action is minimized when the particle is moving in constant velocity. But obviously, we don't really know if of course, if we know Newton's second law, then we know that the physics is the same if we moving in constant velocity with the particle. However, if we are formulating the entire thing in the least action fraction, that's, it doesn't seem obvious. So if in that formulation, is there a way to know that the physics is the same even if we are moving with the particle?
Okay, now we go back to the Lagrangian of a free particle. Now, it means that there are two coordinate systems moving relatively with a uniform velocity. Am I correct? That's what you mean. Am I right? So we can write down the Lagrangian with respect to two coordinate systems, which are moving with respect to each other with a uniform velocity. All right, so we write down the Lagrangian. 1 is equal to 1/2 mv squared, given here, and the other one will be 0, for example, will be 0. All right. Now we differentiate, we write down the Euler-Lagrange equation motion. We'll realize that rank L rank V in both coordinate system will give you a constant as well. One gives you 0, the other one gives you a constant V, right, mv. And this is exactly the first law of motion. Which is the result of the Galilean invariance. Can you follow? Hello? Hello? Okay, anyway, let us take 5 minutes break. And then we'll come back to some examples of Lagrangian mechanics. All right, 5 minutes break. Now, we will look at some examples to help us understand the Lagrangian formulation better. The first example is about projectile motion under gravity in 2 dimensions. All right. Here is the figure it mentioned about, the question is about. So we have a cannonball, we have a cannon here, and it fires a cannonball, right? And the ball flies out and out of the cannon, and is acted upon by the uniform gravity. Okay, we are familiar with this example, and learn it. And actually, we learned this example in high school. So we can write down the kinetic energy and potential energy in Cartesian coordinates first. Okay, so recipe step, the first step of our recipe of Lagrangian formulation is writing down the kinetic energy and potential energy in Cartesian coordinates. So the kinetic energy term consists of two terms. The one depends on x dot, the other one depends on y dot. All right. The potential energy term is equal to mgy. Okay. We take the potential energy equal to 0 at y equal to 0 for convenience. All right. Then L equal to T minus U, the difference between kinetic energy and potential energy. Then we apply the Euler-Lagrange equation motion in x direction and y direction. All right. So in x direction, we have round L round x minus d by dt round L round x dot equal to 0. Okay. Now the first term is equal to 0. Why? Because the potential energy does not depend on x. So the first term gives you 0. The second term gives you x double dot. So the Euler-Lagrange equation motion in the direction x is x double dot equal to 0. In other words, the horizontal component of velocity is constant. The horizontal motion is uniform. All right. Then in y coordinate, we do the same thing. Round L round y, obviously, will give you minus mg. And the second term will give you y double dot. All right. So combine, after simplification, we obtain y double dot equal to minus g. Okay. And this is exactly the same equation based upon Newtonian mechanics. The same equation motion based upon Newtonian mechanics. All right. Now we can also use the polar coordinates to tackle the same problem. Okay. Now this time, the kinetic energy is given by these two terms. Okay. Now we go back to the figure. So here we have r, the radius is increasing, and also the angle is increasing too, is changing too. Okay. So kinetic energy due to radial direction, due to the angular direction. All right. How about the potential energy? Y is equal to r sine theta. Okay. All right. Combine these two together, we have the Lagrangian. So we write down the Euler-Lagrange equation motion in the radial direction, and the Euler-Lagrange equation of motion in the theta direction. In the radial direction, round L round R can come from two terms. The second term here, the second term in the kinetic energy, and the potential energy term. All right. d by dt round L round Ri give you the mr double dot. All right. Combining together, we have this complicated equation motion in radial direction. How about in theta direction? Since only the potential energy depends on theta, so round L round theta gives you minus mgr cosine theta. And this term will give you two terms. The first term, r squared theta double dot, mr squared theta double dot. The other one will be 2mr r dot theta dot. all right? Now, you can see that in this example, choosing coordinate systems, choosing a suitable coordinate system is very important. If we choose Cartesian coordinates, we have a cyclic coordinate, and also we obtain a conserved quantity, the conservation of linear momentum in the x direction. And we can obtain a very simple equation motion in the y direction, all right? However, if we choose the polar coordinates, then we get a too complicated equation motion coupled together, and it's hard for us to identify any conserved quantities because we cannot identify any cyclic coordinates easily. All right. The second example, a particle of mass m is constrained to move on the inside surface of a smooth cone of half angle alpha. Okay, so it's moving around on the surface. The particle is subject to a gravitational force. Its weight. Determine a set of generalized coordinates and determine the constraints. Find the Euler-Lagrange equation motion. Okay, we concentrate here. Now that is the figure. The particle is moving smoothly inside the cone on the surface, on the inner surface of a smooth cone of half angle, all right? Now, in general, we can see that if we use the spherical coordinates, R can change, theta can change, right? Phi can change. So in other words, azimuth angle can change, polar angle can change, and the radius variable will change. And we can easily see that this will give you a mass if we choose spherical coordinates. So we can see that it will be more convenient to choose the cylindrical coordinates as the generalized coordinates, all right? So we have R, theta, and Z, okay? Now we try to write down the kinetic energy. To begin with, we identify the velocity square first. So velocity square is equal to r dot square plus r square theta dot square plus z dot square, all right? And we express these three terms in terms of the radius and theta and also alpha. Now you realize that the alpha is a constant here, all right? It's a constant parameter. So after simplification, we realize that v square is equal to r dot square times cosecant square alpha plus r square theta dot square, all right? Now the potential energy, if we choose u equal to 0 at z equal to 0, then it has a very simple expression, u equal to mgz, all right? Mgz can be expressed as mgr cosine alpha. Again, alpha is a constant, okay? Now we combine the kinetic energy and potential energy together, we get equation 7.28, the Lagrangian function. Now from this expression, you can immediately see that there are only two generalized coordinates, r and theta, right? R and theta. In general, the motion of a single particle in space has 3 coordinates, right? 3 coordinates. However, we have one constraint, i.e., the particle must move on the inner surface of the cone. And the inner surface has an adjacent angle, alpha, with respect to the z-axis, okay? And alpha is a constant. So we should have 3 variables, but with one constraint. So actually, we only have 2 independent coordinates, generalized coordinates, all right? Now, by looking at this, by examining this L a little bit more closely, we realize that it does not depend on theta. In other words, theta is a cyclic coordinate. If theta is a cyclic coordinate, then the corresponding momentum round L round theta dot must be conserved, all right? And we immediately realize that round L round theta dot is equal to mr squared theta dot, which is simply the angular momentum of the particle. So in other words, the cyclic coordinate theta, the existence of the cyclic coordinate theta implies the conservation of angular momentum about the z-axis, all right? So the equation of motion in the theta direction is trivial. Then we look at the Euler-Lagrange equation motion in r direction, in radius, okay? And it is given in equation 7.30. So we have to differentiate L with respect to R. There are 2 terms. First term coming from the kinetic energy, the second term coming from the potential energy, all right? The next term, round L round R dot, there's only one term coming from the kinetic energy, all right? So finally, the equation of motion is given in equation 7.31, all right? We have 2 independent generalized coordinates in this case, and we have 2 Euler-Lagrange equation motion, Euler-Lagrange equation motion, which are coupled together in general, all right? Since the theta coordinate is cyclic, so we have a conserved quantity, which is the angular momentum, all right? Due to this conservation law, then we are left with only one equation of motion in the r direction, given in equation 7.31. Okay. mr squared theta dot is equal to constant. So we can rewrite the second term in equation 7.31 in terms of this conserved quantity, in terms of the angular momentum. All right. And then we have an equation in R only, which is a second order differential equation in R, okay? Involving R. We are not going to solve this equation explicitly. This is not the purpose of this example. Now, the third example, we have a simple pendulum of length B, and its support moves on a massless rim of radius A, okay, rotating with angular velocity omega find the expression for the Cartesian components of velocity and acceleration of mass m. Obtain also the angular acceleration shown in figure 713. So this point of support of this simple pendulum will move around this center at a constant angular velocity omega. Okay. Now, if you are asked to apply the Newton's second law to do this problem, I think it's quite complicated. On the other hand, the Lagrangian formulation will give you a very systematic procedure to write down or to obtain the equation motions. Okay, so step number one, we write down the coordinates in terms of some fundamental independent variables. We write down x equal to a cosine omega t plus b sine theta, all right? The x components of this mass m. Y component, y coordinate is equal to a sine omega t minus b cosine theta, all right? Because the first term is due to, the first term in these two expressions are due to the motion of the support point of support. Then we differentiate both x and y with respect to t to obtain the velocities in x and y direction. Okay. Now, getting the x dot and y dot, we can write down the kinetic energy T. Okay. Kinetic energy T. And the potential energy is very simple too. mgy. We take u equal to 0 and y equal to 0. Okay. X equal to, y equal to 0, the potential energy is equal to 0. Now the Lagrangian is equal to t minus u x dot square is given here, y dot square is given here. So we substitute it into the Lagrangian function and also substitute the y into the Lagrangian function. Then we get this, all right? Now you can see that the fundamental generalized coordinates involves only theta, right? You can see it here. No x, no y, no x dot, no y dot appear in this expression. Only theta and theta dot. Omega is a parameter. So in fact, in this example, there is only one independent generalized coordinate, and that coordinate is theta. All right. Now we apply the Euler-Lagrange equation motion for theta, the first term, round L round theta dot, and then differentiate with respect to t. We get this. Round L round theta, we get this. And combine them together, we get an equation motion in the theta direction. Okay, theta double dot equal to omega square a divided by b cosine theta minus omega t minus g over b sine theta. All right. In the special case that omega is equal to 0, i.e., the point of support is not moving, what will we get? Omega equal to 0. Then we get back the simple pendulum equation motion. All right. Okay. Now, again, it is difficult to solve this equation analytically. So we'll stop here and will not care about solving it. In fact, Let me tell you one thing. In the past, I realized that most students can do pretty well in analytical mechanics rather than in comparison to the first year classical mechanics course. This is a surprise to many of us. Do you know the reason? Most students can do pretty well in analytical mechanics, i.e. Lagrangian mechanics, Hamiltonian mechanics, in comparison to the Newtonian mechanics course in first year. Do you know why? Now, in the first year Newtonian mechanics course, you are asked to write down the Newton's equation of motion, and then you are required to solve these equation of motion explicitly, right? However, in this course, you are taught a set of systematic procedures based on Lagrangian and Hamiltonian to write down or derive the desired equations of motion. All right. After that, your task is completed. You are usually not asked to solve the equations of motions. All right. So it becomes a set of routine procedures to solve problems in Lagrangian mechanics and Hamiltonian mechanics. All right. In Newtonian mechanics, you are actually asked to solve the equation of motion explicitly. You need to find the solutions analytically. However, in this course, most of the problems have very complicated equation of motion, which cannot be solved analytically. So after deriving the desired equation of motions, you are all set. You have finished your duties. So in this sense, this course is much easier than the previous Newtonian mechanics course. All right. All right. How about one more example? In other words, in this course, the mathematical tools are less important in this sense. All right. In fact, later I would try to tell you, I would try to teach you a simple way to obtain approximate solutions to these problems, especially those, especially for the short time duration. All right. Okay, this problem, find the frequency of small oscillations of a simple pendulum placed in a railroad car that has a constant acceleration a in the x direction. Okay, so we look at this example. This train has an acceleration a, all right? And we want to find the equation of motion. So we write down the x coordinate, y coordinate of the particle. So obviously, if we set x equal to 0 and x dot equal to v naught at t equal to 0, then the x at any time t is equal to this. All right. L sine theta is the distance relative to this point, this axis in the train, and the train is moving with uniform acceleration. This is the displacement of the train. All right. This is the distance away from this vertical axis inside the train. All right. How about the y coordinate? There's no motion along the y axis, so y is equal to minus L cosine theta. Now we differentiate x with respect to time and y with respect to time. V naught t gives you V naught. 1/2 AT squared will give you AT. Finally, the last term will give you a term proportional to theta dot. All right. And y dot will give you a term proportional to theta dot 2. Knowing x dot and y dot, we can write down the kinetic energy and also the potential energy. All right. Combining these two, we have the Lagrangian. Okay. Now, in terms of the theta, the Lagrangian looks a bit complicated. However, we realize right away that even though the motion of this particle is in a plane, there is only one independent generalized coordinate. That coordinate is theta, angle theta, right? Then we apply the Euler-Lagrange equation motion to in the theta direction. Okay, round L round theta will give you these two terms on the right hand side. Round L round theta dot, and then differentiate this result with respect to t will give you theta double dot on the left hand side. Okay. Now, to determine the equilibrium position angle, in other words, if there's no motion of the pendulum inside the train, then the double theta dot is equal to 0. All right, no force acting on the particle. The theta double dot will be equal to 0. Okay, so the equilibrium angle is equal to arctangent minus arctangent of A over G. Okay. Now, knowing this equilibrium angle, we can define theta in terms of theta E and a new variable eta. All right. And since we are interested in small angular displacement about the equilibrium angle, so the theta double dot is equal to eta double dot equal to minus G over L sine theta E plus eta minus A over L cosine theta E plus eta. Now, remember that eta is very small, so we can approximate it by taking only the first terms in the Taylor series expansion. All right. So this is a sum of two angles. This is a sum of two angles. We can expand them. And keeping only the leading order term in the definition in cosine eta and sine eta, we get this. Okay. Now, we realize that after simplification, we have an equation given in an equation motion given in 7.40. And this is a very simple equation. Why? Because it is exactly the equation for a simple pendulum, ordinary simple pendulum for small angular displacement, all right? And we can write down the solution right away. The solution must involve cosine and sine function of t, right? And the natural frequency will be given by equation 7.42, okay? That is the natural frequency of this simple harmonic motion. As a double check, if the acceleration, the uniform acceleration of the train is equal to 0, we will get back the canonical example of a simple pendulum. Okay, that is the natural frequency of a simple pendulum at rest. All right. Now, if eta is not small, then we are in trouble. Why? Because if we are asked to solve this equation of motion here or in 7.39, it's tough. No analytical solution can be found, and we have to resort to numerical methods to get numerical solutions. All right. Okay, I think I'll stop here. And do you have any questions? I don't want to rush to. I don't want to rush. So I hope that you can have some time to digest the materials. All right. The problem set number 2 will be uploaded tomorrow, and I will give you enough time to do it. Any questions so far about these examples? Now, let me reiterate. In all these examples, we follow a set of routine procedures. First, identify the position or the x coordinates, y coordinates of the system. All right. And then we re-express these Cartesian coordinates in terms of some more fundamental generalized coordinates. All right. So that some redundant Cartesian coordinates can be eliminated. After doing that, we rewrite the Lagrangian in terms of the fundamental generalized coordinates. The number of generalized coordinates dictate the number of Euler-Lagrange equation motion that can be derived. All right. Once you have derived the Euler-Lagrange the desired Euler-Lagrange equation motion for all the generalized coordinates, then your task is accomplished, is completed. Okay. You are usually not asked to solve the equation of motions because they are usually very complicated and cannot be solved analytically. All right. So keep in mind that you understand the set of rules of deriving the Euler-Lagrange equation motion clearly. Okay. All right. Any questions so far? No questions? 1. No questions? 2. No questions? 3. All right. I'll see you next Tuesday, and problem set number 2 will be uploaded tomorrow. All right. Bye-bye.